and TIFR. This part is not for IIT JAM. Up to this part, it is common. Is it clear?
Yes.
Now, I will discuss the syllabus of each part separately. So first, let's start with electrostatics. Electrostatics part. So in electrostatics, we will talk about electric field due to stationary charges. Field due to stationary charges. Electric field due to stationary charges. You know that charges comes in two varieties. You have positive charge and negative charge. Charges are conserved. Charges have additive property. You can add, for example, if you have plus Q plus 2Q, so total charge will be plus 3Q, or plus Q minus 2Q, you will get minus Q. So you know about the charges. Here we have to see electric field due to stationary charge distribution. So in general, we talk about charge density. Let's say general cases, charge density. We have stationary charge density. So source is stationary charge density. It may be point charge, it may be surface charge, line charge, anything, but I'm talking about the general case. So when stationary charge is given, how to find the electric field? So here we will see what will be electric field. Charge is given, you have to find electric field. We will also talk about electrostatic potential. Charge is given, how to find electrostatic potential. Means rho is given, you can find E. Rho is given, you can find electrostatic potential. When E is given, we can also find charge density. Potential is given, we can find the charge density. Electric field is given, we can find potential. Potential is given, we can find the electric field. If you know this relationship, you know about electrostatics. So I have summarized what we are going to do in electrostatics. We are going to relate all these things: stationary charge, electric field, potential. One is given, you can find other. Is it clear? ठीक है?
Yes, sir.
Now see, so what are the topics? I am discussing the syllabus of electrostatics. So first topic will be when charge is given, how to find electric field. You know that, you know about Coulomb's law. So we will talk about Coulomb's law and superposition principle. So this will be the first topic of electrostatics. And in certain symmetries only, we will find the electric field using Coulomb's law. Now, when there is a three special symmetry like a spherical, cylindrical, and planar, we will use Gauss law. So Gauss law and its applications. So next topic is Gauss law and its applications. In this, we will discuss the concept of electric flux. Electric flux. Then we will talk about electrostatic potential. Electrostatic potential. How to find electrostatic potential. Then we will see next topic will be electrostatic energy. Next topic will be, we will talk about, let's see, Poisson's equation and Laplace equation. Poisson's equation and Laplace equation. Then we will talk about electrostatic energy. Electrostatic energy. We will see total work done in assembling all charges. That will give you the electrostatic energy. Then we will discuss two types of material. One is dielectric or insulator, another is conductor. So we will discuss the properties of conductors separately. Properties of conductors. Then we will talk about electric dipoles. We will define electric dipole. And we will talk about potential and electric field due to dipole. And then we will see dipole in an external field. Dipole in an external field. Then we will talk about polarization. Polarization. Polarization P. And here we will discuss concept of bound charges. Concept of bound charges. Then we will see Gauss law in presence of polarized dielectrics. Gauss law in presence of polarized dielectrics. And then we will talk about electrostatic boundary condition. Electrostatic boundary conditions. V, E vector and D vector. We will talk about boundary condition for potential and electric field E vector and D vector. Is it clear?
Yes, sir.
Now there are two separate topics in electrostatics. One is called as multipole expansion. multipole expansion. So using multipole expansion, we can find electric field due to any arbitrary charge distribution, and that will be approximate field. So we can find approximate potential or electric field due to any arbitrary charge distribution. And then we will discuss the image problem. Image problem. Again, these two topics are not the part of IIT JAM syllabus. This will be only for NET, GATE, JEST and TFR. Not in IIT JAM syllabus. So for IIT JAM exam, you can skip these two topics. But if you want to appear in JEST and TFR, you have to cover the whole syllabus. So this is the syllabus of electrostatics. I will discuss one by one. First electrostatics, I will cover it, then move on to magnetostatics, and then next one. Is it clear? What is the syllabus
That
of
is
electrostatics?
whole syllabus is for CSR net, na?
Yes, that is, I am discussing the whole syllabus, but there are some additional topic for net and gate, so that I am giving you. Otherwise, everything is common. Is it clear?
Yes, sir. Yes.
Means this particular topic is not in IIT JAM. Otherwise, this is for net and gate students. ठीक है? Is it clear? Syllabus is clear?
Okay, sir.
So let's see first topic. This will be Coulomb's law and superposition principle. Coulomb's law and superposition. Coulomb's law and superposition principles. So we will first see what is Coulomb's law and how to find the electric field using Coulomb's law. So let us consider we have a stationary point charge Q. This is stationary point charge. And let's say at any point P, r distance away, you have to find what will be electric field due to this point charge Q. So what we will do, let us place a test charge Q. Q is some test charge. Q is some test charge. And I'm assuming both charges are positive. Both charges are positive. So what will be force experienced by test charge? If charges are of same sign, you will see this will experience force in this direction. Both charges are positive. So you will see when they have like charges repel each other and unlike charges attract each other. So both are positive. So test charge will experience force in this direction, and that force is given by 1 by 4 pi epsilon naught Q into Q by mod r square. So this will give you the magnitude and direction will be r cap. This is the force experienced by test charge Q. And you should note that like charges repel and unlike charges attract each other. Attract each other. So here epsilon naught is called as permittivity of free space. Permittivity of free space. And epsilon naught value is 8.86 10 to power minus 12 Coulomb square per Newton meter square. And for calculation purpose, we can take 1 by 4 pi epsilon naught is approximately 9 into 10 to power 9 in MKS unit. Okay? So this is the force experienced by the test charge Q. Now electric field at point P is given by, this is force per unit test charge. This is force per unit test charge, and it will be given by 1 by 4 pi epsilon naught Q by mod R square inversely proportional to distance square. And if charge is positive, if this charge is positive, field is radially outward. And if charge will be negative, you will see test charge will be attracted towards it. So field direction is radially inward. Is it clear? So when you have a positive charge, so you can represent this field line for positive charge. Let's say if you have a plus Q. For positive charge, field is radially outward, and for negative charge, this will be radially inward. So if you place positive test charge, it will move away from the plus charge. So this will be the direction of field. If you place here, it will move towards it. So force per unit test charge, it will be towards of minus Q charge. So that will be the direction of electric field for negative charge. Is it clear? So this is the field due to point charge Q. 1 by 4 pi epsilon naught Q by mod R square, or simply R square. Mod R is R. You can take mod R is small r. Okay? Is it clear? You all know about Coulomb's law?
Yes, sir.
Now we have to see superposition. If there are n number of charges, what will be the electric field? Now consider set of n charges. Let's consider set of n charges. Let us consider set of n charges, Q1, Q2, and so on, Qn. This is point P. So let's say this vector is R1. This vector is R2. And this vector is Rn. And resultant field, let's say this E is the resultant field. I'm assuming that E is the resultant field at point P. So this resultant field is given by, you have to find field due to individual charges and then take vector sum. That is the superposition principle. So according to superposition principle, resultant field will be vector sum of the individual field. Is it clear? So find the field due to individual charges and then take vector sum. You will see, in order to find the vector sum, what we will do, we will resolve all vectors in two components. Let's say that this is X and Y, and you have E1, you have E2, and so on. Let's say you have En. So you have to resolve all these vectors in two components, Ex and Ey. Just resolve E1, E2, En in X and Y direction, and then Ex will be E1x plus E2x plus and so on Enx. I am writing here plus, but it may be minus also, depending on whether these field lines are in the same direction or opposite. And similarly, Ey is E1y plus E2y plus Eny. So resolve it, find Ex and Ey, and then you will get your resultant field X, Y. And this resultant field is resultant of this field is, let's say, E. And if this makes an angle alpha, so you have already calculated Ex and Ey component. So magnitude of this E vector is given by Ex x cap plus Ey y cap. And then magnitude of E will be given by under root Ex square plus Ey square. And alpha is given by tan inverse Ey by Ex. ठीक है? Is it clear? So we will use the component form to find the resultant field E. It is easy to find the vector sum in X and Y. And then you should write E is Ex x cap, Ey y cap. Is it clear? ठीक है?
Yes, sir.
So please note down. Now this we can write this as 1 by 4 pi epsilon naught summation over I1 to n Qi by mod Ri square Ri cap. ठीक है? This is the vector sum of field to individual charges. Yes or no? ठीक है?
Yes.
Now we will generalize this expression for continuous charge distribution. So let's see. This is for set of n charges, but if you have a continuous charge distribution, for continuous charge distribution. Electric field E is given by, this is 1 by 4 pi epsilon naught. Now you have to summation changes to integration. We will consider an elemental charge dq, and r distance away you will get the electric field. So this is the generalized form of Coulomb's law for continuous charge distribution. Is it clear? Coulomb's law for continuous charge distribution. But now we have to see what will be this integral. So depending on situation, it may be line integral, surface integral, or volume integral. So we have line charges. Let's see, we can distribute charges either as a line charge, surface charge, or volume charge. So we have line charges. And this line charge is given by lambda. Lambda is charge per unit length. Lambda is charge per unit length. So let us assume total charge Q is uniformly distributed over a length of wire. Over L length, charge Q is distributed, and let's say it is distributed uniformly. So lambda is given by Q by L. And if it is a uniform distribution, lambda is constant, and we say that distribution is uniform. This is uniform line charge. If lambda is not constant, it is varying with the distance, then we will say that it has non-uniform charge distribution. It has non-uniform charge distribution. And you have to find the field due to this line charge. What you will do, you have to consider an elemental length dl, and in this charge dq will be lambda dl. And at any point P, r distance away, we can write the Coulomb's law as E is 1 by 4 pi epsilon naught. Now dq is given by lambda dl. dq is lambda dl by mod r square r cap, and here you have a line integral. Okay? This will be the Coulomb's law for line charges. Is it clear? So you have to consider line integral here. Now let's see, this is for line charges. Coulomb's law for line charges. Now we will see surface charge. surface charge is sigma. And this sigma is charge per unit area. Sigma is charge per unit area. So charge is distributed over the surface. Let us consider we have some surface S whose area is A and charge Q is uniformly distributed over this surface. Total charge is Q and that is distributed over this surface. So sigma will be given by Q by A. And this is constant. So this distribution is uniform. And if sigma is function of R, we say that distribution is non-uniform. So if you have to find field due to this, we have to consider an elemental area dA. And in this elemental area, charge dq will be sigma dA. And at any point P, again r distance away, if you have to define electric field, this will be given by 1 by 4 pi epsilon naught surface integral sigma dA by mod r square r cap. This is Coulomb's law for surface charges. ठीक है?
Yes, sir.
Now we will see volume charges. Now we will see third one is volume charge. Volume charges. So volume charge is specified by rho. Rho is charge density. So rho is charge per unit volume. This is charge density, charge per unit volume. Charge per unit volume. Sigma is surface charge, charge per unit area. Volume charge is charge per unit volume. So charge is distributed throughout the volume. Let's say you have this particular volume V, and in this charge, total charge is Q. Total charge is Q, that is distributed throughout the volume. So if distribution is uniform, this is Q by V. V is volume, charge per unit volume. If this is constant, we say that distribution is uniform. Is it correct? And if rho is function of R, we say that distribution is non-uniform. So it means charge may be distributed uniformly or it may be distributed non-uniformly. And again, if you have to find field due to this volume charge, So this elemental volume is d tau, and in this charge is dq is given by now rho d tau. And if you have to see electric field at point P, so this electric field is given by 1/4 pi epsilon naught volume integral rho d tau by mod r square r cap. This is the Coulomb's law for volume charges. ठीक है? I am simply defining the Coulomb's law for discrete charges, continuous charges, and also for volume charges. Yes or no?
Yes, sir.
Now we have to represent our Coulomb's law for this charge density in our coordinate notation. So let's see what coordinate notation we are going to use. Coordinate notation. Because this source point and field point, they are represented by some position vector. So we have to identify those position vectors. So we will use this coordinate system. If this is X, this is Y, and this is Z. Let's see, this is the source point where charge is located. And this source point is position vector is X dash, Y dash, Z dash. And this position vector is given by vector R dash. Then there will be a field point. Now this coordinate is X, Y, Z. And this is the separation vector R. This position vector is small r. So field source point is represented by its position vector R dash, and field point is represented by position vector R. And you know that R is given by XX cap plus YY cap plus ZZ cap. R dash is given by X dash X cap plus Y dash Y cap, Z dash Z cap. And this R dash plus R is, so this will give you separation vector R. R is the separation vector. This will be given by R minus R dash. So you can call it as separation vector. This is separation vector. So this will be X minus X dash X cap Z minus Z dash Z cap. It means distance between source point and field point. This will be represented by the separation vector R. So we are going to use this coordinate notation. So if you want to write your Coulomb's law in our coordinate notation, what we will do, we will write E to be function of R. E to be function of R, because field point is function of R. And then rho is function of R dash. Source point is function of R dash. Just to distinguish between source point and field point, we are taking these notation. And I am taking volume integral d tau dash represents the source. But actual field depends on distance between source point and field point. So we have represented our Coulomb's law in our coordinate notation in this form. This is the representation of Coulomb's law in our coordinate notation. So throughout electricity and magnetism, we are going to use this coordinate notation. Is it correct? Yes or no?
Yes.
Yes, sir.
So we have just defined the continuous charges. Now we will see example based on Coulomb's law. So we will first see for discrete charges, and mainly question are asked based on the continuous charge distribution. Okay? Is it clear? Any doubt in Coulomb's law?
No, sir.
Okay? Chalo. Now let's take examples. First example, consider we have a 2-point charge Q and both charges are positive. D distance above the center of these charges, they are at 2L distance apart, and this is the center of these two charges. What will be electric field at point P? Can you find? Can you find the electric field? Try to calculate. Try करो. So you have to find field due to individual charges, and then you have to take vector sum. So let's say this is charge 1 and this is charge 2. So this charge is positive. What will be electric field at this point? This is given by E1. And let's say this distance is small r. So magnitude of E1 will be given by 1 by 4 pi epsilon naught Q by R square. This is the magnitude, and where R is given by under root L square plus D square. In same way, if you find field due to this charge, so this will be E2, and this is also same distance away. And magnitude of E2 is also same. Magnitude of E2 is same as magnitude of E1. ठीक है? Now, let's assume this angle is theta. So this angle is also theta. And then assume this is XY plane. Now you have to resolve E1 and E2 in component form. Let's resolve E1 and E2 in component form and then find the resultant. Find the resultant of E1 and E2. So this will give you, if you resolve it, this component is E1 cos theta. And this component is E1 sin theta. Similarly, this component is E2 cos theta. And this component is E2 sin theta. Yes or no? Now you will see these two components will cancel because they have same magnitude and they are in opposite direction. Yes or no? So
Yes, sir.
if you see the resultant in x direction, what will be resultant in x direction? It will be 0. E1 sin theta, E2 sin theta, they will cancel each other. So Ex will be 0. And what will be Ey? This is given by twice of E1 cos theta because E2, E1 is same. So resultant is in the y direction. So E1 is 1 by 4 pi epsilon naught q by r square. And what is cos theta? Cos theta will be given by d by r. Cos theta is d by r. So finally, if you write this electric field, this is 1 by 4 pi epsilon naught by r cube L square plus d square power 3 by 2, and direction is y cap. So this will be the electric field. Is it correct?
Yes, sir.
This is the resultant electric field due to these two positive charge. Yes or no? Is it clear? ये ठीक है?
Yes, sir.
Now let's assume one charge is negative. You have same charge distribution, but only thing is now this charge is negative. Can you find electric field at this point?
Sir, Ex equals to 0 and Ey equals to twice E1.
Because in y direction you have E1 cos theta, E2 cos theta, E1, E2 magnitude same, so they will add up. In x direction they will cancel out. They are of same magnitude.
Okay, sir.
In same way, find electric field due to this charge configuration. Try karo. So again we have to find let's see this is positive charge, so this will be field E1. This is negative charge, so this will be E2. E2 will be towards the minus Q charge. This angle is theta, this is also theta. So magnitude of E1 is same as magnitude of E2. This is R. So 1 by 4 pi epsilon naught Q by R square R cap. Let's see the magnitude only. Direction we know E1 and E2, where R is under root L square plus D square. R is under root L square plus D square. Now you have to find the vector sum. Let's see the vector sum of E1 and E2. So again, I am taking this to be X and this to be Y. So if you resolve E1 in this direction, so this is E1 cos theta. And this will be E1 sin theta. E1 cos theta and E1 sin theta. If you resolve E2 in this direction, this will be E2 cos theta. And this will be E2 sin theta. ठीक है? Is it clear?
Yes.
Yes, sir.
Now what will be the resultant in Y direction? E1, E2 magnitude is same. So now in this case, in Y direction it will cancel out. So EY will be 0. And what will be EX? EX will be 2E1 sin theta. And this is 2, 1 by 4 pi epsilon naught Q by R square. Sin theta is L by small r. So resultant field E will be given by 1 by 4 pi epsilon naught 2QL by R cube. And R cube is L square plus D square power 3 by 2. And direction will be X cap. This is the field. Is it clear?
Yes.
Yes, sir.
Now let's see under one approximation. If you assume that this D is, if you assume that D is far greater than L, means you are seeing this charge distribution far away from these two charges. So what will happen? Just see, then electric field will be given by 1 by 4 pi epsilon naught so you can neglect this L. So this is 2QL by neglect L. So this will be DQ X cap. Now see, dependence of the electric field is 1 by distance cube, not a square. Because now it will look like a dipole. And we will discuss the case of dipole where electric field is varies as 1 by distance cube. So Under this approximation, it acts like a electric dipole. Yes or no?
Yes, sir.
ठीक है? So
हाँ, sir.
under this approximation, it looks like a dipole. Dipole case I will discuss separately. So in this way, let's see, I have taken these two cases where we have find the field due to individual charge, and then you have to find the vector sum, superposition principle. And for vector sum, you have to resolve field along x and y direction so that you can easily write the electric field. Okay? Is it clear? Yes or no?
Yes, sir.
Yes, sir.
Can I take next example?
Yes, sir.
Now take another example. Consider three charges. This is Q, this is 2Q, and this is 3Q. This is L, and this is also L distance away. What will be electric field at the fourth corner? What will be this electric field? So this is, let's say this is first charge, this is second charge, and this is third charge. You will see this length will be also L, and this is under root 2L. So what will be field due to charge 1? This will be E1. All are positive charge. This field will be E2. And this field will be E3. And then we have to resolve this in XY plane. Yes or no?
Yes, sir.
So what will be magnitude of E1 and E3 is same? No, magnitude of E1 is 1 by 4 pi epsilon naught Q by L square. Magnitude of E2 is 1 by 4 pi epsilon naught 2Q by under root 2 L square 1 by 4 pi epsilon naught Q by L square. And magnitude of E3 is 1 by 4 pi epsilon naught Q by L, 3Q by L square. So just see, E2, E1 magnitude is same. E1 and E2, they are same. And E3 is different. Now you have to resolve E1 and E2, E1, E2, E3 in X and Y component. What will be X and Y component? You have to see EX and EY component of the field. So EX will be given by what? Magnitude of E1, and this angle is 45 degree because it's a square. This is also 45 degree. So you will get mod E2 cos 45. And projection of E3 along X will be 0 because angle is 90 degree. So this is EX. And what will be EY? EY is mod E3 plus mod E2 sine 45. Just resolve into component. E1 component along E3 will be 0. So you will get EX and EY. Yes or no? You will get EX and EY. So let's say this is the resultant field E, which makes an angle alpha with x-axis. So magnitude of E you can calculate as under root EX square plus EY square. EX, EY is known, so you can find it. And then direction with respect to x is given by tan inverse EY by EX. For numerical value, if you everything is given Q and L, then you should get the numerical value. Otherwise, magnitude is EX square plus EY under root. Alpha is tan inverse EY by EX. Is it clear?
Sir, EX equals to mod of E1 plus mod of E2 equals.
E2 cos phi. You have to resolve E1, E2, E3 along this. So this is mod E1, its component is cos phi, and this component will be 0. Component of E3 will be 0 because cos 90, this angle is 90 degree. Similarly, when you say EY, this is E1 component will be 0. So mod E3, E2 sine 45 and plus this will be 0. Yes or
Yes,
no?
sir. Yes, sir.
So you have to resolve, even you have n number of field, resolve along x and y and see the resultant in x and y. If n x and y they are in the same direction, you should add. If they are in opposite direction, you have to subtract. So for discrete charges, find the field due to individual charges and then take vector sum. You will apply the superposition and that will give you the resultant field. Yes or no?
Yes, sir.
Yes, sir.
So at this level, questions are mainly asked from continuous charge distribution. I have given you the Coulomb's law and I have taken 3 examples for discrete charges. In same way, if even more charges are given, you can find. But we have to mainly see continuous charge distribution, especially case of a wire, case of a ring, and case of a disk. So in second lecture, we will focus on continuous charge distribution. Okay? Is it clear?
Yes, sir.
So wait for 15 minutes. At 6:30, I will start with field due to continuous charge distribution. Clear?
Yes, sir.
Yes, sir.
So wait for 15 minutes.